Good morning. Welcome to the 13th edition of the EDPR University Challenge Award Ceremony. First of all, I hope that everyone is safe. Just like the previous edition, and due to the current situation, the event will be held online. The theme for this year's edition of EDPR University Challenge is EDPR and Renewable Energies, a future side by side with a focus on renewable energies and sustainability. Now, let's focus on the awards ceremony. During the event, we will get to know the 15 projects that have made it to the semifinals. Then, we will announce the top 5 teams, and finally, the top 3 EDPR University Challenge teams. The ceremony will be organized as follows. We will begin by watching the pre-recording of the 2-minute elevator pitch from the 15 semifinalist groups. After the break and the jury's deliberation, the top 5 teams will be announced. Each top 5 team will have to give a 5-minute presentation and may have to answer a few questions from the jury. Finally, we will announce the top 3 teams and the winner of the EDPR University Challenge 2021. Before we continue, it is my pleasure to introduce you to the members of the jury who are joining us today. Joaquín García Boto, Development Director of EDPR Spain. Luis Manuel Santos, Head of Innovation at EDP Spain. Telmo Vieira, Managing Partner of Premio Valor Consulting. Ignacio Huisi, Business Development Officer at InnoEnergy, Spain. Enrique Doeijo, Director of Risk Advisory, Energy Economic Consulting at Deloitte, España. Welcome all members of the jury. As this is a local final, it has unfortunately not been possible to have all the teams with us today. However, we do have all the semifinalists here, and I'd like to take this opportunity to express our appreciation for the effort and enthusiasm shown by all participants, especially in the current context. You have made this initiative a true success. Let me now introduce you to Rafael Solis, EDPR's Director of Corporate Communication and Stakeholders Management. He'll be explaining why EDPR drives and promotes these kind of initiatives. Go ahead.
And also the ceremony today, is digital for the second year in a row, which doesn't mean that we don't want to organize this physical, because I personally believe that physical events has a plus. It's also encouraging to me see that the University Challenge Award is still going on for the 13th year. It's a long time. I remember still, in 2009, back 2009, where we started together with Telmo. It was a small award, and this year we had, despite the pandemic, 80 projects coming from 100 groups of universities all across Europe, which, as he was saying, is very encouraging. Therefore, I would like to thank you, Premio Valor Consulting, that has been here with us since the beginning, and also InnoEnergy for helping to keep on going with this award. And also, why not? I mean, obviously highlighting the creativity of all the students and teachers, because without them, this wouldn't be impossible. Okay, so at the beginning, I was telling you that I was going to speak as well about innovation. Innovation is at the heart of University Challenge, as is clear, but it's also at the heart of EDP renewals. And let me give you two brief examples. The first one, and I think I mentioned it last year as well, is WindFloat Atlantic. Is the first floating wind farm that exists in continental Europe, and that has been operating for the first year now. It reached 75 gigawatts hour in the first year of operations. And you know, it's an iconic project for us that we would like to scale soon in other geographies. And also, let me put as an example of innovation, the business unit that we have created ad hoc for hydrogen. As a matter of fact, only yesterday, we signed an agreement with Repsol to develop this kind of technology. So we believe it will have an impact in the industry. But you know, for EDP Renewables, it's not only about business. We have strong values in terms of ECG. So it's not only about the financial part of the company, but also about creating let's say, a better tomorrow for future generations. And University Challenge is really part of this. This, let's say, is part of our culture. We believe that through this program, through this award, we create links between the academic and the professional world, and we want to keep on going in this direction. So with any further ado, congratulations to all the group for being here today. Good luck with your presentations, and thank you very much.
Thank you, Rafael, for telling us more about the EDPR University Challenge. Now that we know what the EDPR University Challenge represents, it's time to take a look at the top 15 groups presenting their elevator pitches. The elevator pitch consists on a brief 2-minute presentation during which each team will briefly explain the key aspects of their project. So let's begin then. I would like to welcome to the first team from University, Escuela Politécnica de Ingeniería de Gijón, Universidad de Oviedo. Project, Smart EV Charging Point. Members, Javier Vázquez Álvarez, Alonso Mena Elguera. Professor, Manuel Rico Secades. Let's hear about the project, guys.
Everyone, we are Javier Vázquez and Alonso Mena, students of Electronics Engineer and Marketing, and we are going to present our Smart EV Charger. First of all, I wanted to introduce the context where we want to fit our product. This context is related with the growing market of renewable energy and electric vehicles. Our proposal is a new type of EV charger with capability to manage renewable energy and the energy from the utility company, such as EDP. The system is also ready to incorporate energy storage system, especially once the EV recycled batteries penetrate the market.
This prototype has already been built and tested, and the hardware is ready to handle up to 2 EVs using different control strategies. The user can set the maximum power, always up to 7.4 kilowatts, or decide to charge the vehicles with the energy generated by the solar panels. The user could also program the period of time to charge, taking advantage of the cheaper cost of the energy at night, for example. But more complex solutions can also be developed in the field of Internet of Energy, like taking the energy only from the home battery or limiting the power according to the utility's preferences. All these possibilities can be programmed with an interface panel that the user would have at home. With this interface, the user can not only program the charge, but also see the energy and the power flow of his house. The communication between the charger and the interface is done via Wi-Fi through Mqtt Protocol. With this system, we can also measure and store the information of the user in a database, compatible with big data strategies. We also wanted to mention that our interface is already developed and running a demonstration program, having communication between the Mqtt broker and the microcontroller of the charger. The next step would be to develop a mobile app with the same features that the interface.
This idea is totally feasible, compatible with the MIBI EDP plan, and ready for the next generation of EV chargers and energy management.
Thank you so much for your attention.
Thank you very much and well done. We will now meet the second team coming from Universitat Politècnica de Catalunya, Project Income, Predimensioning Support for Energy Communities based on Photovoltaic Generation. Members, Vincent Casanova Revilla, Kim Espadalé Bonet, Joan Sebastià Guas Mas, Professor Roberto Villafáfila Robles. So we're excited to see the project.
Good morning. We are Vicente Casanovas, Joan Guas, and Kim Espadalé, and we present the ENCOM software for predimensioning energy communities based on photovoltaic generation. The objective of the project is to justify the energetic and economic viability of energetic communities based on photovoltaic generation and with connection to the grid, with simple application so that any user can use it. This program is intended for an individual or company interested in joining an energy community or creating a new one. It can also be used by the administration for public projects or as an energy awareness tool for citizens.
ENCOM is programmed in MATLAB environment, which allows generating a PDF report with the most significant energy and economic results from a simple and intuitive data entry. The result report also provides data on the environmental benefits of implementing the energy community. This software is now applicable in Spain, on the Peninsular Territory and the Balearic Islands. The main objective of the program is to minimize the payback years of the design of an energy community by optimizing the photovoltaic and storage system.
It's been possible to demonstrate through the software that the implementation of energy communities with a solar fraction of around 20% results in some years of amortization below the years of life of the installation, at least with situations where it's not used any storage system. The factors that most influence the variability of these amortization years are the location, due to the solar resource, and the climate, the price of energy, and the efficiency strategies in the consumption. And for communities with a storage system, this currently represents a very high cost per unit of stored energy, which is one of the points for improvement in the future. In the end, ENCOM software can be used for all the people who want to join energy projects around an energy community, providing them with a simple and intuitive tool to be able to check the energy and economic viability of these kinds of projects.
Thank you very much.
Thank you very much, and well done. The next team comes from Universidad Politécnica de Madrid. Project Thermosolar Power Plant with Thermal Storage plus Hybridization with Auto-Produced Hydrogen. Member, Luis Martín, Tomás Borchet, Jan Sado. Professor, Alberto Abadanes Velasco. Let's hear about the project.
Well, our project is a thermosolar power plant with thermal storage plus hybridization with auto-produced hydrogen. Okay, the main objective of our project is to have a zero-emission power plant that produces hydrogen and carbon and can work through the whole year 24/7. How do we get that? First, we're going to talk about the thermosolar power plant with thermal storage. In this chapter, the solar radiation is reflected through thousands of meters to the tower receiver. Through the tower flows liquid molten salts, which are stored in big tanks. The heated molten salts then flow through a heat exchanger and warm up water into steam, which then flows through a steam turbine to produce electricity. So it's a brief explanation. This is already standard technology. We're not changing anything in this part. What we're adding the hydrogen production. How do we do that? First, we need to know that hydrogen is produced. We're producing it through methane. Methane is CH4, which we're converting to hydrogen and carbon. How do we do that? We need for that an endothermic reaction, which we need heat. How do we get it, the heat? From our sodium calcinate. Why? Because of its melting temperature and fusion temperature. We have a lot of range to work, and it's perfect. Comparing it to other calcinate substances. The bubble column reactor. In order to divide, well, the methane pyrolysis takes place in the bubble column reactor. The methane is injected through the sodium calcinate layer, and from this process you obtain hydrogen and solid carbon. In order to do the hydrogen, you need okay, the new plant scheme adding this new technology would be adding the H2 the hydrogen connection, and with a tube shell exchanger, and then the hydrogen turbine. We're also adding a hydrogen turbine to the system. With the hydrogen we produce, we can actually use it, and we can have 24/7 usage. This would be the new scheme with the hydrogen production and the new gas turbine. And the conclusion, we're producing hydrogen, carbon, coal.
Very good. Next up is the team from University, Escuela Politécnica de Ingeniería de Gijón, Universidad de Oviedo. Project, characterization of the mechanical behavior of steels in order to ensure safe design of components for service under high hydrogen pressure. Members, Paloma Álvarez Yáñez, Sergio Rodríguez García. Professor, Francisco Javier Belunce Varela. So, all right, let's hear about the project.
Welcome. This work was performed at the University of Oviedo. The European Union has decided to attain zero carbon emissions by 2050, and green hydrogen obtained from renewable sources will help to get this goal. On this context, infrastructures to store and transport hydrogen shall be constructed with appropriate materials. Hydrogen atoms enter into the structure of the steel when it is submitted to high hydrogen pressure. They diffuse and accumulate in central microstructural regions, giving rise to brittle failure under low stresses. Steels that use to store hydrogen may be mechanically characterized in presence of hydrogen. There are different ways to introduce hydrogen onto steels. One way are the in-situ hydrogen charging tests under high pressure, but there are a very expensive tests and there are only a few testing facilities. Another way could be performing mechanical tests on hydrogen charged tests on hydrogen pre-charged specimens, but these tests gave non-conservative results. So we propose to perform in situ tests using electrochemical hydrogen charging for an acid solution. Hydrogen content can be precisely controlled by means of the cathodic density current. The qualification procedure for steels that work under high hydrogen pressures follow this step. First, hydrogen saturation in the steel under the study pressure may be determined. Then the cathodic density current that introduces onto the steel the exact same hydrogen content may be found. And finally, the selected mechanical test with simultaneous hydrogen charging under such conditions may be performed. Maximum admissible stress levels determined. This operative procedure has low costs and is readily available as it uses only conventional testing machines. Thank you.
Well done, thank you. Our fifth team comes from University, UPC Barcelona, Spain, TU Eindhoven, Netherlands, ESADE, Spain, AG8, Poland. Project, Waste to Hydrogen, an innovative clean energy vector. Members, Natasha Guido, David Ojimba, Marta Censaro. Let's take a closer look at the project.
Hello, this is Team 2726, and I'm David.
I'm Marta.
And I'm Natasha.
And we're here to introduce you to an innovative pathway for waste to hydrogen.
They say renewable energy is the future, yet their intermittent nature and the difficulty to switch completely to electricity make them not perfect. Hydrogen is a clean energy vector that can support the transition into renewables, but our capacity is far behind our demand. On the other hand, we have an abundance of wastewater. Did you know it has been estimated that for every liter of domestic wastewater, up to 7.6 kilojoules of energy can be obtained? We need sustainable ways to tap into this gold mine for the energy transition. Mother Nature provides us with a solution. Microbes that break down organic sugars, releasing electric charge and hydroxide ions. In an electrolytic cell, with air as the cathode, the hydroxide ions recombine to create clean water. This is the microbial fuel cell. Modifying this cell to trap hydrogen from the hydroxide ions creates a microbial electrolytic cell, an alternative to conventional electrolyzers, but this requires some additional electrical power. Compared to worldwide utilities, our unique solution uses a combination of microbial fuel and electrolytic cells to produce green hydrogen from wastewater. The fuel cell provides the energy for hydrogen generation, making it completely energy independent. This innovative characteristic allows us to reduce CO2 emissions, empower people through clean water production, and provide cheaper green hydrogen production. This is where EDP can participate in the hydrogen economy with lower capital and operating costs. How do we know this? Our feasibility study shows that by selling the generated hydrogen, we get a payback of 6 years with an IRR of 9%. Also, the market has few competitors and is expected to grow to $18 million in 2025. Together with us, this is the right moment for EDP to act and establish itself as the pioneer for waste hydrogen.
Thank you. Well done. Now we're going to hear from the team coming from Universidad de León, project More Than Repowering, Nothing is Waste. Members, Antonio Fernández Martín, Aaron Carnicero Mayo. Professor, David Borge Diaz. Let's hear about the project.
Good morning. We are Aaron Carnicero and Antonio Aníbal Fernández, both students at the University of León, and we are presenting our innovative proposal for sustainable repowering, a solution that combines wind, solar, and biomass energy. Our project develops a new system and processes that will produce positive impacts on the environment, boost economic growth, and ensures social development in the affected areas, using a pioneer and innovative business and technology scheme, as we develop new potential lines of research. Our objective is to take the current technology to new horizons that will ensure sustainable, cost-effective, and accessible energy. We propose this innovative idea to reach the previous targets, combining repowering existing wind farms with solar and biomass energy. In the flowchart, we can see that the energy produced by the wind solar realization can be injected to the power grid or used for biomass conversion processes to produce biochar that can be used in other industries or like energetic vector. Both grid injection and biochar ensure economic feasibility and allows a cost reduction on global energy supply. The basis of the project is to support green energy and the circular economy without neglecting the environmental and social impact, providing maximum efficiency in all fields in order to move towards a better future. With the research work, we conclude, we promote novel research lines, think to our innovative ideas and create a new viable business, both by improving the actual system and opening new horizons, always looking at minimum environmental impact and maximum land use sustainability. The solution boosts the local society and business and reduces external energy dependency, considering electricity prices nowadays. As energy engineers, we acknowledge the EDP compromise with renewable energy and sustainability. We propose a solution to contribute to renewable energy share, knowing the future demands and the ongoing electricity dependency of society, especially as green produced electricity. Thank you for your time and consideration.
Good job. We're now going to meet the next team from University, Escuela de Ingeniería de Minas, Energía y Materiales de Oviedo, Universidad de Oviedo. Project, Green Hydrogen, Generation by Hydrolysis driven by excess wind energy production. Members, Paula García Hortal, Sara González Fernández, Silvia Gómez Cardín. Professor, Guillermo Laine Cuervo. Let's see what the group has in store for us.
Hello everyone, my name is Sarah and my team and I are going to provide a solution to one of today's biggest energy problems. Do you imagine a world without the greenhouse gases emissions, a cleaner and a greener energy at a lower cost? That is closer than we think, and the solution lies in hydrogen. Our project is the answer to make this reality possible. Now we are going to introduce you the problem. To understand what we have already said before, it is necessary to point out two things. The first one is the energy required to produce the hydrogen. Hydrogen requires a huge amount of energy to be produced. In fact, the energy required to produce it is greater than the energy obtained using it. And the second one is the wind energy excess. They are going to become more popular and common in the future due to the strong investment that is going to be done in the renewable energy sector. This project will apply the second problem to the first one, solving both of them at the same time. But how? We are going to show you the solution. Rainwater will be recollected in a building roof and stored in tanks. The wind energy excess is going to be used to produce the electrolysis process. This is how we are going to produce green hydrogen at a lower cost. We truly believe that our project is capable enough to be carried out in a short period of time with low investment and, of course, with incredible profit opportunities. Thank you for your attention.
Thank you for the presentation. Let's continue now. The next team comes from University, UPC Barcelona, Spain, KTH Royal Institute of Technology, Sweden, ESADE, Spain. Project, Domestic Batteries to Help Balance the Grid. Members, Pere Albello, Roger Izquierdo, Sergi Nogueira. Professor, Mónica Aragués Peñalba. Let's hear about the project.
We are Pere Albello, Roger Izquierdo, and Sergi Nogueira, and we're going to present to you Battery.
Have you noticed the dramatic increase in electricity price during this month? Have you ever considered buying a battery, but its high price bagged you out?
We, the battery team, want to present to you an innovative method for taking advantage of the increasing renewable energy variability and the growing amount of electric vehicles in our roads. Listen carefully, because your electricity bill is about to get cheaper. Here is our proposal. By creating a distributed energy storage system and using a smart control, while we're using these postcard batteries, we will be providing ancillary services for the transmission system operator that, combined with a smart algorithm, will make you save on the electricity bill.
From Battery, we're going to make all of this possible by means of this extremely simple business model. Investments will be made into purchasing and repurposing used electric car batteries that will be installed into our customers' households with no upfront costs. They will save on their bills by always consuming the cheapest electricity and will repay us via a monthly subscription fee. Finally, leveraging our installed capacity in the form of a virtual power plant, the grid operators will be paying for the balancing services that we will be prepared to offer.
As you may imagine, everyone is interested in saving money, so the potential batteries market is wide. We will firstly be focusing on Spain and Portugal, but without losing sight of the whole European market. This is our team, and thank you very much for your attention.
Well done. The 10th team comes from Universidad de Castilla-La Mancha, project Distributed Storage of Wind Power Using Alternating Current Batteries. Members, Juan Enrique Guada Núñez, Javier Cayetano Guada Núñez, Professor Juan Andrés Guada Gil. Let's hear the projects.
Good afternoon. I am Juan Enrique Gualda, and I'm going to present my team's project, Distributed Storage of Wind Power Using Alternating Current Batteries. Introduction. Renewable energies require the support of the storage system to avoid clean energy waste in valley period. It is observed in this graphic that some wind power plants, colored in green, must be disconnected at midnight because there is an excess of energy production. Here, a distributed wind power storage system is proposed to avoid this energy loss by using alternating current batteries and also electric cars. A main and new characteristic of this report is that the battery charger is not required. The price of the electricity is growing and growing. To lower it, it is necessary to use more and more wind power plants. Alternating current batteries. An alternating current battery consists of a direct current battery connected to an inverter. During valley hours, the battery is charged at the expense of the network, and during peak hours, it injects energy back into the network again. Parallel connection. This is the basic scheme along with this phasor diagram. Alpha is the advanced angle of the inverter's voltage with respect to that of the grid. If alpha is greater than 0, the inverter works as such. If alpha is lower than 0, the inverter works as a rectifier. There is then no need for the rectifier. The economic saving is significant. Implementation plan. The implementation plan is composed of two phases: prototype construction, laboratory testing to check the theoretical basis, and application. Initial promotion with advertising on TV, and the state will implement new electricity rates. Conclusions. Distributed storage will take place in homes, industries, and shops. For storage, alternative current batteries and electric cars are used. The inverter is also going to work as a rectifier, avoiding the need for the latter. With this storage system for 1 million users, 3.5 power plants of 1,000 megawatts could be avoided. Thank you very much for your attention.
Thank you and good work. The next semi-finalist team to present comes from the University, Facultad de Biología, University of Oviedo. Project, integration of a biohydrogen production system with the sludge line of a wastewater treatment plant. Members, Álvaro Gutiérrez Rodríguez, David Pacho Marrón, Pedro Riesgo Espinosa. Professor, Sergio Collado Alonso. Let's see the project.
Good morning to everybody, and thanks you all for being here today. I'm Álvaro Gutiérrez, and I'm going to expose our project, integration of a biohydrogen production system in the sludge line of a wastewater treatment plant. To start with, we would like to say that the world energy consumption has been rising during the last decades, meaning that, in addition to the expensive sludge management, the issues why we believe our project to be necessary. Moreover, with this idea, we produce a green and renewable energy, cutting down the carbon emissions related to fossil fuels, while at the same time treating a polluting residue with no use these days. Here, we show a flowchart with the layout of our system, where we can see our anaerobic reactor where a group of microorganisms carry out the process. Regarding the benefits this idea may provide, we would like to say that the more relevant ones are the achievement of a more stable waste material with a reduced organic load, the improvement of the social perception of the plant, which is no longer only a treatment plant as it starts to produce green energy, the economic benefit for the plant, usually deficient, and the production of green and renewable energy. Now, we would like to highlight the economic balance of our project, where we prove it to be profitable in the short term. For the plant uses a model, the Villa Pérez wastewater treatment plant, the estimated net benefits are of 16,000 euros per year. Moreover, we would like to say that there are several potential clients that have publicly announced their interest in purchasing this type of energy. To sum up, our project began as a new way of generating green and renewable energy from a cheap and abundant type of waste, which currently has no productive use. It does require a relatively low initial investment with a short payback period, and it would result in savings for plants. In addition to this, as future perspectives, we also would like to say that this technology could be applied and extended to other parts of our country, generating a greater amount of hydrogen while treating their sludge in a better way. And that's all. Thank you all for your attention.
Thank you very much. The next team comes from University, UPC, Spain, KTH, Royal Institute of Technology, Sweden, École Polytechnique, France. Project, modeling of an offshore wind farm that is hydrogen generation and storage. The members are Celia Gordon, François Ducosset, Alfonso Cana. The professor, Mónica Aragués Peñalba. Let's take a closer look at the project.
Today we're presenting Fuel Winds, a model of an offshore wind farm combined with onshore hydrogen generation and storage. With increasing share of offshore wind in the energy mix, serious problems arise. The biggest one is the intermittency, which is mainly due to the variation on wind speeds. This difficulty ends up having serious issues in matching electricity demand with electricity generation. The most common scenario is the overproduction of energy, which leads to wind curtailment and to a decrease on market prices. Our solution to this problem is a model of a joint offshore wind farm with an alkaline electrolyzer and a solid oxide fuel cell. As such, the surpluses of the wind farm that would else need to be curtailed would be used to produce and store hydrogen with the electrolyzer. Then this hydrogen would be converted into electricity with the fuel cell when the demand is not satisfied. The model is based on a piece of code that determines when to convert the surplus of energy from the wind farm into hydrogen and when to convert this stored hydrogen back into electricity. In this graph, it can be seen how non-renewable sources are quickly replaced by hydrogen-generated energy once the hydrogen storage builds up. Our proposal will be beneficial as it's a forecast of a full renewable energy scenario, which will provide the consequent projection. The amount of the generated hydrogen, the amount of energy generated from hydrogen, and the wind power needed to generate this energy. Finally, this project will imply an 80% increase of renewables and a 6% decrease of non-renewables in the Spanish electricity mix. Moreover, the two LCOEs prove the economic feasibility of our project. Thank you very much for listening to this presentation.
Thank you and well done. The next project was carried out by students from University Politecnico di Milano, Italy. Project Decarbonized Maritime Transport, an innovative infrastructure based on wind power and liquid hydrogen. Members, Michelle Grassi, Sofia Gandolfi, Nabil Mohammed. Professor, Gianluca Valenti. Let's hear about the project.
Decarbonization. What exactly comes to your mind when you think of this word? Well, for most of us, it is either electric cars or solar panels. But don't you think that we also need to decarbonize our oceans just like we are decarbonizing our lands? So the three of us came together, thought of this problem, and we are here to propose a solution. Thanks to the increased globalization, the shipping sector already contributes to 2.5% to the global greenhouse gas emissions. And if no mitigations are done, it can only increase to 17% by 2050. So what actions can we take?
We propose an innovative solution which comprehends offshore wind turbines that will power an electrolyzer which produce hydrogen. This hydrogen will be then liquefied to increase its energy density and used by the ships to refuel. So our methodology comprehends a review of the state-of-the-art technologies, the determination of the most strategical places, and a technical and economic evaluation. In particular, we focus on the Europe-Asia shipping routes, that is about 30% of global maritime routes. And due to the long distance coupled with low density liquid hydrogen, we will see that 5 refueling steps will be needed.
We analyzed 2 different scenarios. In the first one, new platforms are used, whereas in the second one, refurbished oil and gas platforms are used. We will see that in the second scenarios, initial investment are sharply reduced. We performed an economic analysis and we found out that with liquid hydrogen price of €8 per kilogram, we obtain a discount payback of 12 years, which is a very reasonable value for the energy sector. Our project is replicable and rescalable, and it can be implemented in other regions of the world. We thank you for being with us. We hope that we can work together to implement it in other parts of the world. Let's sail toward a greener future together. From Sofia, Nabil, and Michele is everything. Thank you all.
And good job. Let's now welcome the team from University, Escuela Politécnica de Ingeniería de Gijón, Universidad de Oviedo. Project Rewind, viability study for the reutilization of wind turbine blades at the end of their service life through alternative energy generation methods. Members, Pelayo Iglesias de Rueda, Mario Martín Blanco. Professor, Miguel Muñiz Calvente. All right, let's hear about the project.
Hi, we are Mario Martín and Pelayo Iglesias, and we want to present the Rewind project.
Wind turbine technology arose mainly in the early 1990s. Since then, wind farms have grown exponentially. As an example, more than 21,000 wind turbines have been installed only in Spain. Nowadays, in Europe, we have hundreds of thousands of blades at their service life limit, meaning that they must be dismantled. The blades are made by fiber composites, so that a problem appears derived from the impossibility to recycle them. The turbine's blades are being piled up underground, so we are having an escalation in waste production. Relevant people in the field have been pointing out this problem. We propose an innovative solution, the Rewind project. We propose to reuse the blades in situ, taking advantage of the existing wind farm's electric installation. The blades would be used to generate electricity based on von Karman vortices, by inducing oscillating forces synchronized with the structure's natural frequencies. We found a way to optimize those oscillations, and therefore electric energy production is maximized. The Rewind project is completely aligned with EDP and European Union's 2030 carbon neutrality objectives, because it's offering a solution based on the circularity of the wind energy technology, by using the wind turbine blades for their original purpose, to generate energy.
This project proposal reduces wind turbines, wind farm location scouting costs, and environmental costs through the utilization of wind turbine blades to keep producing energy and therefore generate value by giving them a second life. Furthermore, this project could create a new market based on a circular economy while being a renewable energy source. Hand in hand with EDP, this project would be a strong candidate to receive European Union funding through the European New Green Deal because Rewind is aligned with their objectives. In this way, we could significantly reduce the research and development costs this project could need.
And we want to emphasize that the biggest cost of the project is the opportunity cost of not doing it. Thanks for your attention.
Thank you very much. Let's continue now. The next team comes from Universidad Politécnica de Madrid. Project, production of green hydrogen with wave energy. Members, Gonzalo Pérez de Blas, Adela Ballester, José María Bonilla Prieto. Professor, Alberto Abadenes Velasco. Let's hear about the project.
Good morning, my name is Gonzalo, and our project is about the production of green hydrogen with wave energy. Our project is based on the generation of electricity from wave energy through a buoy technology called point absorber, but this technology has several constraints. There is still a low degree of development. It is needed wires to connect the system to the grid. There's an irregularity in the electricity generation of this technology, and the maintenance and the investment costs are pretty high. So our solution is to use this electricity for the production of green hydrogen. By this, we correct the irregularity in electricity production, and we offer an economical and environmental friendly solution, and we can take advantage of the gas pipelines to transport the hydrogen. This is the case study we have done in the coast of Galicia in Spain. We have made an estimation of the annual energy production, taking into consideration the number of buoys, their capacity, their disponibility factor, having a value of 7,190 megawatts hour, that with the electrolysis considered, it is produced 131 tons per year of hydrogen. So with this, hydrogen could be used for industrial, transport, portable devices, or large-scale applications. So the project attraction comes from its competitive price in the market and its low environment impact. Furthermore, it will improve by the time with the upcoming investigations, development, and innovation of the technology. In fact, the project is even more profitable when we combine the use of electricity with the production of hydrogen and for injecting it into the grid depending on the electrical system necessities. We can see as well a prediction of the two implantation phases in 3 and 2 years. Finally, these are our conclusions.
Thank you very much. We now welcome the last semi-finalist team from University Instituto Superior Técnico, Portugal, Grenoble ENP Institute of Technology, France, Uppsala Universitet, Sweden. Project, new integrated energy solution based on hybrid for renewable energy network. Members, Brandon Vargas Vera, Joao Saldana. Professor, Elena Ramos. Let's see what the group has in store for us.
A new energy concept is proposed to integrate different renewable energy sources as well to support the net zero carbonization, to accelerate energy transition, to increase the energy system flexibility and sustainability. This innovative solution is a hybrid for renewable energy network, Hy4Ren. In order to have a 100% renewable energy friendly world, we need all renewable energy sources to work together. Hyper-Rain combines hydropower and pump storage, floating solar PV, wind power, wave energy, and energy storage in batteries. In this industry, this is a complete game changer. It's the first project of this type in the world. It is completely eco-friendly, modular, scalable, and versatile. Hyper-Rain, the best of 4 energy sources.
We are Hyper-Rain, and we're here to present our new integrated energy solution. There's no point in presenting a solution as elegant as ours if there's no problem to be solved. We intend to address the biggest issues that we face nowadays: centralization of energy generation, fossil fuel dependency, and the intermittency of energy supply from renewable sources. As seen in the video, our project consists in a combination of 4 renewable energy conversion technologies. We offer the client a scalable and flexible solution, low maintenance and cost-effective hybrid solution that allows the user to be fully independent from the grid. Among the several benefits, we highlight the very low investment, option to decarbonize energy-intensive industries, and also possible applications in desalinization and hydrogen production projects. We are Hyper-Rain, and we want you to help us build the future with this modular solution of today. Thank you.
Thank you. You all have done a great job. So we will now have a break of approximately 15 minutes. The jury will deliberate and choose the 5 finalists who will then make a 5-minute presentation so that we can learn more about their projects. I kindly ask you to keep track of the time so that at 11:40 we can proceed with the ceremony. Thank you very much and see you in a bit.
This is a new way of generating energy and an important step to fight against climate change. Portugal enters in a new era with an international acclaimed solution in the production of offshore renewable energy. The Wind Float Atlantic project, formed by Ocean Winds, Repsol and Principal Power, is the first floating wind farm in continental Europe just off the coast of Viana do Castelo. This floating wind farm will allow the optimization of natural resources and will speed up the commercial deployment of this innovative technology. Wind Float Atlantic is an example of a more sustainable future for mankind, with the largest turbines ever installed on floating platforms. The total installed capacity of 25 megawatts will provide sufficient energy to 60,000 people throughout the year. This energy promises an endless source. The potential of wind is immense, and this renewable energy is an essential part of the worldwide decarbonization strategy, free of CO2 emissions. The Wind Float Atlantic project is the future we envision. Our mission has begun, and we will continue to nurture the power of nature to make our planet more sustainable. This is the beginning of a new era committed to enabling a better future. Wind Float Atlantic. Energy beyond the horizon.
The world has changed. I feel it in the water. I feel it in the earth. I smell it in the air. A new power is traveling all around the earth. A clean and infinite energy in constant renovation that comes from natural sources such as the sun, the wind, and the human will. Yes, the world has changed. I feel it everywhere. Many men and women have started to go in a new direction, innovating to make humankind grow while nature is preserved. This community is EDPR's people. We are present in 15 countries, and together we have increased the production of natural energy, generating 29 terawatts-hour, avoiding 18.5 million tons of CO2 emissions, and growing day by day to achieve a wealthy business while contributing to a cleaner air. That's the result of putting together the nature power and a total trust in people's energy. Our energy is more than 1,700 employees from 32 nationalities. Our partners, shareholders, clients, the communities that live happier through our social, economical, and environmental initiatives. Now, we are a bigger company with a stronger capacity. The sun, the wind, and the sea help us in our aim. They don't need to change, but we, humans, must keep evolving, and we have to do it now. We must do it together, because our mission is not just the EDPR's mission. It's the future that we all deserve. It's time to join our community, the community of change.
From today onwards, the sun will shine in a different way. It's about to be transformed into clean, renewable energy. And that energy will improve the lives of thousands of people. The planet can't wait any longer. Here at EDP Group, we're doing our bit. We're a global energy company committed to leading the energy transition and improving the lives of current and future generations. EDP Renewables is launching the company's latest solar complex in Brazil. Pereira Barreto Solar Complex is the largest in operation in São Paulo State and the 5th largest in Brazil. The complex covers a total of 455 hectares and can generate up to 547,000 megawatts-hour per year. That's enough to power a city of approximately 750,000 people. In just 1 year, the photovoltaic complex will stop more than 150,000 tons of CO2 from being emitted into the atmosphere. It'll also make a lasting contribution to the region's social and economic development. At EDP, we believe that a sustainable future begins with the choices we make today. And we're changing tomorrow now.
This is a new way of generating energy. and an important step to fight against climate change. Portugal enters in a new era with an international acclaimed solution in the production of offshore renewable energy. The Wind-Float Atlantic project, formed by Ocean Winds, Repsol and Principal Power, is the first floating wind farm in continental Europe just off the coast of Viana do Castelo. This floating wind farm will allow the optimization of natural resources and will speed up the commercial deployment of this innovative technology. Wind-Float Atlantic is an example of a more sustainable future for mankind, with the largest turbines ever installed on floating platforms. The total installed capacity of 25 megawatts will provide sufficient energy to 60,000 people throughout the year. This energy promises an endless source. The potential of wind is immense, and this renewable energy is an essential part of the worldwide decarbonization strategy, free of CO2 emissions. The Wind-Float Atlantic project is the future we envision. Our mission has begun, and we will continue to nurture the power of nature to make our planet more sustainable. This is the beginning of a new era committed to enabling a better future. Wind-Float Atlantic. Energy beyond the horizon.
The world has changed. I feel it in the water. I feel it in the earth. I smell it in the air. A new power is traveling all around the Earth. A clean and infinite energy in constant renovation that comes from natural sources such as the sun, the wind, and the human will. Yes, the world has changed. I feel it everywhere. Many men and women have started to go in a new direction, innovating to make humankind grow while nature is preserved. This community is EDPR's people. We are present in 15 countries, and together we have increased the production of natural energy, generating 29 terawatts-hour, avoiding 18.5 million tons of CO2 emissions, and growing day by day to achieve a wealthy business while contributing to a cleaner air. That's the result of putting together the nature power and a total trust in people's energy. Our energy is more than 1,700 employees from 32 nationalities. Our partners, shareholders, clients, the communities that live happier through our social, economical, and environmental initiatives. Now, we are a bigger company with a stronger capacity. The sun, the wind, and the sea help us in our aim. They don't need to change, but we, humans, must keep evolving, and we have to do it now. We must do it together, because our mission is not just the EDPR's mission. It's the future that we all deserve. It's time to join our community, the community of change.
From today onwards, the sun will shine in a different way. It's about to be transformed into clean, renewable energy. And that energy will improve the lives of thousands of people. The planet can't wait any longer. Here at EDP Group, we're doing our bit. We're a global energy company committed to leading the energy transition and improving the lives of current and future generations. EDP Renewables is launching the company's latest solar complex in Brazil. Pereira Barreto Solar Complex is the largest in operation in São Paulo state and the 5th largest in Brazil. The complex covers a total of 455 hectares and can generate up to 547,000 megawatts hour per year. That's enough to power a city of approximately 750,000 people. In just 1 year, the photovoltaic complex will stop more than 150,000 tons of CO2 from being emitted into the atmosphere. It'll also make a lasting contribution to the region's social and economic development. At EDP, we believe that a sustainable future begins with the choices we make today. And we're changing tomorrow now.
This is a new way of generating energy and an important step to fight against climate change. Portugal enters in a new era with an international acclaimed solution in the production of offshore renewable energy. The Wind Float Atlantic project, formed by Ocean Winds, Repsol and Principal Power, is the first floating wind farm in continental Europe just off the coast of Viana do Castelo. This floating wind farm will allow the optimization of natural resources and will speed up the commercial deployment of this innovative technology. Wind Float Atlantic is an example of a more sustainable future for mankind, with the largest turbines ever installed on floating platforms. The total installed capacity of 25 megawatts will provide sufficient energy to 60,000 people throughout the year. This energy promises an endless source. The potential of wind is immense, and this renewable energy is an essential part of the worldwide decarbonization strategy, free of CO2 emissions. The Wind Float Atlantic project is the future we envision. Our mission has begun, and we will continue to nurture the power of nature to make our planet more sustainable. This is the beginning of a new era committed to enabling a better future. Wind Float Atlantic. Energy beyond the horizon.
The world has changed. I feel it in the water. I feel it in the earth. I smell it in the air. a new power is traveling all around the Earth. A clean and infinite energy in constant renovation that comes from natural sources such as the sun, the wind, and the human will. Yes, the world has changed. I feel it everywhere. Many men and women have started to go in a new direction, innovating to make humankind grow while nature is preserved. This community is EDPR's people. We are present in 15 countries, and together we have increased the production of natural energy, generating 29 terawatts-hour, avoiding 18.5 million tons of CO2 emissions, and growing day by day to achieve a wealthy business while contributing to a cleaner air. That's the result of putting together the nature power and a total trust in people's energy. Our energy is more than 1,700 employees from 32 nationalities. Our partners, shareholders, clients, the communities that live happier through our social, economical, and environmental initiatives. Now, we are a bigger company with a stronger capacity. The sun, the wind, and the sea help us in our aim. They don't need to change, but we, humans, must keep evolving, and we have to do it now. We must do it together, because our mission is not just the EDPR's mission. It's the future that we all deserve. It's time to join our community, the community of change.
From today onwards, the sun will shine in a different way. It's about to be transformed into clean, renewable energy. And that energy will improve the lives of thousands of people. The planet can't wait any longer. Here at EDP Group, we're doing our bit. We're a global energy company committed to leading the energy transition and improving the lives of current and future generations. EDP Renewables is launching the company's latest solar complex in Brazil. Pereira Barreto Solar Complex is the largest in operation in São Paulo state and the 5th largest in Brazil. The complex covers a total of 455 hectares and can generate up to 547,000 megawatts-hour per year. That's enough to power a city of approximately 750,000 people. In just 1 year, the photovoltaic complex will stop more than 150,000 tons of CO2 from being emitted into the atmosphere. It'll also make a lasting contribution to the region's social and economic development. At EDP, we believe that a sustainable future begins with the choices we make today. And we're changing tomorrow now.
This is a new way of generating energy and an important step to fight against climate change. Portugal enters in a new era with an international acclaimed solution in the production of offshore renewable energy. The Wind-Float Atlantic project, formed by Ocean Winds, Repsol and Principal Power, is the first floating wind farm in continental Europe just off the coast of Viana do Castelo. This floating wind farm will allow the optimization of natural resources and will speed up the commercial deployment of this innovative technology. WindFloat Atlantic is an example of a more sustainable future for mankind, with the largest turbines ever installed on floating platforms. The total installed capacity of 25 megawatts will provide sufficient energy to 60,000 people throughout the year. This energy promises an endless source. The potential of wind is immense, and this renewable energy is an essential part of the worldwide decarbonization strategy, free of CO2 emissions. The WindFloat Atlantic project is the future we envision. Our mission has begun, and we will continue to nurture the power of nature to make our planet more sustainable. This is the beginning of a new era committed to enabling a better future. WindFloat Atlantic. Energy beyond the horizon.
The world has changed. I feel it in the water. I feel it in the earth. I smell it in the air. A new power is traveling all around the earth. A clean and infinite energy in constant renovation that comes from natural sources such as the sun, the wind, and the human will. Yes, the world has changed. I feel it everywhere. Many men and women have started to go in a new direction, innovating to make humankind grow while nature is preserved. This community is EDPR's people. We are present in 15 countries, and together we have increased the production of natural energy, generating 29 terawatts-hour, avoiding 18.5 million tons of CO2 emissions, and growing day by day to achieve a wealthy business while contributing to a cleaner air. That's the result of putting together the nature power and a total trust in people's energy. Our energy is more than 1,700 employees from 32 nationalities. Our partners, shareholders, clients, the communities that live happier through our social, economical, and environmental initiatives.
Now, welcome back to the 13th edition of the EDPR University Challenge Awards ceremony. It seems that the jury has already decided on this edition's top 5 projects. Before we find out which projects have made it to the 5-minute presentation round, I would like to present the jury's spokesperson, who will give a brief talk on the selection process. Please welcome Dr. Ignacio Huisi, Business Development Officer at InnoEnergy Spain. Ignacio?
Thank you. Good morning, everyone. It's time now to know the 5 top projects. First of all, on behalf of the jury I have the pleasure to be part of, I would like to thank all groups who have taken part in the contest for their work and contribution in the developing of the renewable energy sector. I would also like to stress the value of these 5 projects I'm about to announce, not only for their quality, but also for their likelihood to become real. As you are aware, all projects have been assessed in accordance with the criteria set out in the contest terms and conditions. The aspects considered included defining the problem, the methodology, the creativity, and the innovation. We have found all projects to have both positive and negative aspects. weaknesses, and strengths. But the key decision factor was, without doubt, the practical approach of these top 5 I'm about to announce. These 5 groups will have the opportunity to showcase their projects in a 5-minute presentation. Let's go. We have no drama. Smart EV charging point from Universidad Politécnica de Ingeniería de Gijón, Universidad de Oviedo. ENCOM, pre-dimensioning software for energy communities based on photovoltaic generation, Universidad Politécnica de Catalunya. Waste to hydrogen, an innovative clean energy vector from UPC Barcelona, Spain, and TUE Eindhoven, Netherlands, and ESADE, Spain, and AGH, Poland. Rewind, viability study for the reutilization of wind turbine blades at the end of their service life through alternative energy generation methods. Escuela Politécnica de Ingeniería de Gijón, Universidad de Oviedo. And finally, new integrated energy solution based on hybrid for renewable energy network. Instituto Superior Técnico, Portugal, Grenoble INP, Institute of Technology, and France, Uppsala University, Sweden. The host will now call on you one by one so you can present your projects. Congratulations to the top 5 selected and all the rest for the hard work. Thank you.
Thank you, Ignacio. And now that the jury has chosen its top 5 projects, we will start with the second round of presentations so we can gain additional insights into those projects. This second phase consists of a 5-minute pitch, after which the jury may ask some clarifying questions. At 4 minutes and 30 seconds, you will hear the sound of a wind turbine like this. When you start to hear this sound, uninterruptedly, it means your 5 minutes are up. So let's start then. The first top 5 team is University, Escuela Politécnica de Ingeniería de Gijón, Universidad de Oviedo. Project, Smart EV Charging Point. Members, Javier Vázquez Álvarez, Alonso Mena Elguera. Professor, Manuel Rico Secades. Congratulations.
Good morning. Okay, let's see if I can. All right, I have the control. Good morning, everyone. We appreciate this opportunity to being able to give a deeper explanation of our idea.
In the next years, the way of production of energy that we're used to is going to completely change. It's already well known the profitability of installing solar panels at home, profitability that will be increased in the short term with the cheaper cost of the panels, and the penetration in the market of recycled EV batteries for storage. Although big-scale energy production will be always necessary, most of the homes of small local consumers will follow this structure, and they will play a main role in the production of energy. This extraordinary change is a trend we cannot miss, and that's why we want to hear with our smart EV charging point.
So our project it's not just to develop a simple EV charger. We want to go beyond and create a whole system of energy management for home. But how are we going to achieve this? Well, we measure at every moment the energy generated by the photovoltaic panels and the energy consumed by the house and the EVs. So we can use different control strategies according to this information, always in the field of Internet of Energy. We want the user to be aware and decide about the production and distribution of this energy. So far, we have implemented 3 different charging modes. The first one, the user can set the maximum power, always up to 7.4 kilowatts. The user could also decide only with the solar energy generated on his roof, with the solar charge. A periodic charge is implemented as well, for routines or night charge, which is perfect solution for both the user, who takes advantage of the cheaper cost of the energy at night, and the utility company to balance the grid load during off-peak hours. But more complex charging possibilities can be developed in the prototype as well. For example, if both cars are charging, we could balance the energy given to them depending on their state of charge. So the one with lower battery will receive more power. A home storage battery can also be implemented in the structure. With this change, we could take the energy from the battery using different structures, always covering our needs. And we could also adopt in the future bidirectional charge, adopting vehicle-to-grid or vehicle-to-home technologies, where our vehicle is now the one who gives the energy to power our home. To summarize, endless possibilities can be developed using smart grid techniques. In this picture, we can see the prototype we have developed. The PCB with the current sensors to measure the power flow, and the microcontroller, who is the brain of the whole system and is connected to the Wi-Fi network. As we can see, the size is very compact, so we could fit in a small box easily. We have developed an interface panel that the user would have at home. This interface is wirelessly connected to the charger, and with it, the user can initiate or finish the charge, as well as to program the different control strategies of the charger. But not only that, in the screen, it is also displayed the energy flow of the house, so the user is aware at every moment of the energy production and consumption of his house. This interface is very intuitive, suitable for all kinds of users, and even the ones who have a low knowledge in the subject. To communicate the charger and the interface, we have chosen Mqtt Protocol, transmitted via Wi-Fi, which is perfect for projects of Internet of Things. So far, we have a demonstration program running between the interface and the charger, both connected with a Mqtt broker that we have installed. And this broker organizes the communication in both directions. The system is also ideal to store information of power consumption and charging routines, so multiple big data applications can be implemented. The next step would be to develop a mobile app with the same features than the interface, but without so the user doesn't have to be at home. This app would be connected also to the same Mqtt broker, having communication with both the charger and the interface. As we said previously, the project is realistic and feasible, so it goes in line with the EDPR plan, and it is ready for the next generation of smart grids and EV charger. Thank you for your attention.
Thank you. And now, do the members of the jury have any questions? No questions? No questions. Well, the second top 5 team.
Question.
Yes. Thank you, Ignacio. I have one question regarding the use of this charger for vehicle-to-grid applications. Have you considered any array of different algorithms in order to take into account this double wave function of the charger?
Well, no, actually, in the moment, it's just an idea for future possibilities, but we haven't seriously taking it into account and consider different algorithms or technologies. We haven't studied on deeply yet.
Okay, thank you.
I have a question too.
Yes.
So thank you for the presentation, Javier.
Thank you.
In all those technologies that you want to basically mix together, what do you think you're going to focus? What is going to be your own technology, and what can be integrated from other technologies from others?
Well, I think our own technology would be to have everything on the same interface. For example, imagine the user is in the kitchen or in the living room with this big screen, on always knowing the energy flow, the state of the charge, if it is charging, if it is not. And yeah, what it is different from the rest of the chargers is this big screen and the capability of say, okay, I just want now to have a good production. It is a very sunny day, and I want to charge only with the solar energy. Or no, if I have a battery, I want to store this energy in a battery, and for the night, I want the charge to be charged with the energy that it is storing now in the battery. So I think that combination of everything is the perfect solution for the next term, in the short term future.
So you're going to focus on the software side and then probably take hardware from other players.
I know actually the hardware is not it's not quite difficult. I mean, the most difficult part of the project is the software. Yeah.
Okay. Thank you.
All right, so no more questions. The second top 5 team to present their project is from Universitat Politècnica de Catalunya, project ENCOM, Redimensioning Software for Energy Communities Based on Photovoltaic Generation. Members are Vincent Casanova Revilla, Kim Espada Bonet, Joan Sebastián Guasmas. Professor Roberto Villa Fáfila Robles. Congratulations. Go ahead.
Okay. Good morning. First, I will try if that works. I cannot move the presentation. Okay, now. Sorry. Good morning, everybody. I'm Kim Espadale, and I will do the extended presentation about the ENCOM software. First of all, since in the first 2 minutes presentation, we have already explained the main ENCOM functionalities, we'll focus now on developing an example of an energy community application using ENCOM, our software. Just as a reminder, ENCOM is a software that tries to justify the energy and economic viability of energy communities based on photovoltaic generation and with connection to the grid with a simple application. The example that we present tries to offer a predimensioning of an energy community in Lugo, a city located in the northwest of Spain. The location has a North Atlantic climate, so the conditions of solar resource and heating consumption are among the most extreme in the Iberian Peninsula. The community will be located in a residential area with a crop file and an industrial warehouse nearby. Based on the fact that there's a large surface available for the installation of solar panels, the software will perform a predimensioning of the optimal installation, deciding if it's viable or not, and if it should have a storage system. In relation to the inputs, this example will take into account a purchase price of energy of 13 cents per kilowatt hour and a price of injected energy of 7 cents per kilowatt hour. On the consumption parameters community, we'll have in the community 15 houses and 10 flats in the North Atlantic climate zone, and an industrial warehouse with a consumption of 35 kilowatts hour day and the irrigation of 5 hectares of crop file. The generation priority, which affects the angle of inclination of the panels, will be considered for winter, where the consumption is higher and the solar resource is minimal. Then the user will be able to choose the model of solar panels and batteries from among the models available in the software database. With the models of batteries and solar panels already defined, it results in 9.5 years of amortization of the installation, taken as the best option to have a storage system in this case. Apart from these results, all the results offered by the software, included this graphic also, are presented in a PDF report. This graph shows the variation of the years of amortization in function of different levels of storage. The installation has been sized with 86 solar panels, 24 battery modules, and an annual solar fraction of 21% for all the community. In this graph, you can see the energy distribution of photovoltaic generation in a typical day for each month. That directly consumes solar energy is showed in blue. In red is the stored solar energy, and in yellow is the grid injected energy. This other graphic, also available in the report, shows the annual energy distribution of energy communities consumption. The purple sector represents the solar energy directly consumed. The yellow sector represents the energy stored and then consumed. And finally, the blue one is the energy consumed directly from the grid. So here we can take the 21% of the solar fraction. Then regarding the economic results, ENCOM presents the most significant parameters. We can see how the total investment to be made is close to 28,000 euros. The annual remuneration for energy injection to the grid is about 420 euros. And we obtain an annual savings thanks to the implementation of the software of about almost 3,000 euros per year. Then the savings in CO2 emissions, thanks to the implementation of the community, is about 3.5 tons of CO2 per year. This graphic is also available in the report, in the results report. Okay. The factors that most influence the viability of these amortization years are the location, due to the solar resource and the climate, the price of energy, and the efficiency strategies in the consumption. In the end, ENCOM software can be used for all people who want to join energy projects around energy community, providing them with a simple and intuitive tool to be able to check the energy and economic viability of these kinds of projects. So thank you very much for your attention, and from all the group, thanks also for this opportunity. And if you have any question.
Thank you. And yeah, any questions from the jury?
I have, well, first of all, congratulations for your nice project. I have a question concerning the financials of your project. So you presented an estimate of costs. Can you please indicate how you could reach those estimate of costs?
Of course. As I said, we have a database with different models of batteries and solar panels. So depending on the model, we take one cost or another one. And then for the inversors, regulators, and other electrical machines, we did a market study, and we made a graphic that defines the power of those machines with the price depending on the power. So depending on the size of the community of the instrument, we reach one price or another one. And then for the cost about the construction of the community and all these things, we used typified models. All are referenced in the project. So.
Okay, just one additional comment. When we are making economic and financial analysis, there is something that it's important also to consider, which is called externalities. So for example, if your project has a CO2 reduction, you should by somehow to try to measure this and incorporate this also in your economic analysis. Because what happened in some cases, projects are not viable just by itself, but when you consider the positive impact of externalities, then they become stronger viable. Okay, it's just a comment in terms of economic evaluation of projects. Okay.
Okay.
Thank you.
Thank you.
Yes, I have another question. According to the Spanish law, all members of a local energy community have to be inside a circle with the center at the local renewable generation and in a radius of 500 meters. Haven't you considered this geographical limitation in the analysis?
No, not the geographical restrictions. We use the base of the legislation in the Spanish law, but we took some different considerations in some points because for us we could see that for bigger communities the age of amortizations are a bit less. And in the conclusions of the project, we also say that maybe for the really viability of this kind of projects, the legislation might change in some of the points. And one maybe is that one, is the area restriction.
This geographical restriction is a very strong one because it limits your availability of consumers according to the initial point where you have located the PV panel of any other renewable energy source. So I think it's quite a strong limitation that it made jeopardize the success of a local energy community. So I think it's one of the strongest variables so far when considering the deployment of local energy communities.
Okay, thank you.
Do you estimate in your tool the internal rate of return of the project? And if you estimate, have you compared the situation with batteries and without batteries?
Yeah. Yeah, so in the graphic of one of the slides, the first is the first graphic is to compare with different amount of batteries, different amount of storage, the changing of the years of amortization. So the program takes the optimal one. So if it's the optimal one is to have the no storage system, the program take it without storage system. But if the program compares the results and see that the storage system is the optimal one, then takes that one.
But well, obviously with the time of amortization of the project, you can estimate the internal rate of return. Obviously, if you have that the project you recovered investment in 10 years, you have more or less the internal rate of return on 7%. But my perception in this kind of projects is that usually the battery reduces the internal rate of return of the project. So it's a penalty for the project. I don't know if you have the same perception.
Yeah, we in the written project we also put it this point that with the batteries, then the years of life of the installation it's less. So without batteries, the communities also are also have a higher years of amortization. A lower years of amortization in comparison with the years of the installation. Only in the case with the without the storage system. Yeah.
Thank you.
Sorry, my question, I think Telmo has arised the same question. Basically, I'm interested on the calculations also. How, if you took into account total cost, I mean, in terms of the licenses, the cost of the licenses, and all the things that you need to do to make it happen, basically. I know that varies from community to community, but I think that's important to really take into account total cost. Have you done that in the example?
Yeah, no, maybe in the example, we only have with 5 minutes to show the inputs and then the outputs, but the algorithm also explained in the written project takes into account lots of different points for the cost calculations, and not only the machines, also the work to install them.
Okay.
So yeah.
Okay, thank you.
Thank you for all your questions. The next team is from University UPC Barcelona, Spain, TUE Eindhoven, Netherlands, ESADE, Spain, AGH pollen, waste to hydrogen, and innovative clean energy vector. Members are Natasha Widow, David Ojimba, Marta Sensaro. Congratulations. Let's start the 5-minute presentation.
Yes, good afternoon, everyone. So we are Natasha, David, and Marta. We are from the InnoEnergy Select program, and we are here today to tell you more on our innovative proposal, Waste to Hydrogen. Okay, so a quick recap on today's situation. In order to support the integration of renewables energy, we are still lacking up to 56 gigawatt of electrolyzer capacity by 2030. And on the other side, we have an abundance of wastewater with potential energy that are not utilized yet. So seeing this amazing potential, we decided to conduct a feasibility study. Yeah, so what we did is we started from research, market analysis, and then sizing and financing based on a case study. And finally, a business model to show how EDP can implement this technology in real life. Our proposed technology is composed of two cells, so the microbial fuel cell and the microbial electrolysis cell. With the help of microorganisms, we are able to break down wastewater into hydrogen, which requires very little energy. If you see here, it only requires 0.11 volt of energy input, which is less than 10% of what a regular electrolyzer requires to produce 1 molecule of hydrogen. Now, when we compare these hydrogen generation technologies with the others, the slide is not working. Okay, sorry. Okay, now when we compare it with the other technologies, we can say it's the most innovative. Why? Because it has a low energy input and therefore it has the highest efficiency for hydrogen generation. We see it has the most potential for both industrial and domestic use. And not to mention that it is a niche market that is open to disruption. So what makes our technology unique? We would like to highlight 3 main points here. First, as mentioned in our previous slides and also the 2-minute pitch, is the ability to be energy independent. By combining the two cells, the fuel cell is able to provide the energy for the hydrogen generation, sustaining itself. Next, the technology is sustainable in many points of view. It has less energy losses, and also it uses wastewater as fuel itself, tackling global issues of waste. And third, it is not location dependent, so it can be implemented anywhere, including rural and remote areas. Our technology brings a well-rounded impact for EDP and people's daily life. So starting from environmental impact, by both saving the electricity that was supposed to be used for wastewater treatment and the hydrogen production, a substantial amount of CO2 is reduced by introducing our solution. And economical-wise, we are able to produce green hydrogen much cheaper than today's common technologies, which will be explained further in the financing study. Socially, with this clean water production, which can be implemented in rural areas, people's well-being will be improved. Now let's dive into our case study. To validate our business idea, we considered how EDP could work with Barcelona's Baix Llobregat wastewater treatment plant by replacing part of their current capacity with our technology. First, what we did was we calculated the amount of potential energy available based on the current system capacity. Then, we tried to size the reactor based on the technology available and do a cash flow model from there. The results of our cash flow projection shows that with a capacity of 15,000 meter cubic per day from the wastewater plants, we can achieve a payback period of 6 years and an internalized return of rate 9%. And here I would like to highlight the levelized cost of hydrogen is 2.8 euro per kilogram, while according to NREL, nowadays the average LCOH is 3.8 euro per kilogram. So taking a look at this growing global microbial fuel cell market, currently existing players in this market have small scale. So this is where EDP can come in. upscaling pilot projects into industrial scale applications. Our business proposal to EDP is to use waste to hydrogen. So therefore, EDP can offer hydrogen as an energy factor, which will be cheaper and also less energy intensive. The hydrogen can be sold to sectors that are hard to electrify, such as the transportation sectors or existing chemical industries that use hydrogen. A key partner here in the business model is the wastewater treatment plants, where the reactors will be placed. So the initial cost that will be required is the reactor itself, transportation and storage costs for the hydrogen. From there, we can already sell green hydrogen as the main revenue.
Thank you very much. Time's up. Members of the jury, any questions for this team?
Yes, I have a question. My question regards the balance between the amount of power of electricity that is demanded by a conventional electrolyzer versus this microbial fuel cell. So to sort what amount of electricity is less necessary?
Yes, so based on the literature review that we did, they did a comparison between electrolyzers and also this microbial fuel cell. They require much less energy because the microbial fuel cell gives the initial electricity input. So once it's already inputted, like it can sustain itself afterwards because the fuel cell then like gives the energy to the electrolysis cell. So they complement each other and they sustain afterwards, which is why it can be much less than regular electrolyzers that require like a full electricity to break down the water into hydrogen molecules all the time. That's the main difference.
And can you provide us with some estimates about this reduction in the amount of electricity versus the conventional electrolyzer?
So our data here says that it's 0.11. Sorry, if I get your question right, it's comparing with the comparing our technology with general electrolyzers, right?
Exactly.
The fault input. So yeah, here we have 0.11 volt for our technology, and for regular ones is 11 volt, more or less, yes.
Okay, and I have a second question regarding materials used in this microbial fuel cell. This technology requires the use of membranes or this kind of materials that are used in some conventional electrolyzers.
The membranes. Okay, let me check. So if we see the structure of the electrolysis cell, it also requires membrane, but the difference is the membranes are already used in the fuel cells. Yeah.
So what I'm trying to understand is how different is this technology from the conventional technology of electrolyzer or conventional fuel cell?
Yeah, I see. So like the conventional electrolyzers requires an energy, an electricity input to break down the water into hydrogen and oxygen molecules. But here, what it does is we only have water, and then with the help of the microorganisms, they already break down the water. So there is no electricity required, but they require like the initial jump start, something like this to actually electrolyze it. That's the main difference.
Okay, thank you.
With reference to the last question of Luis, my understanding is that in the case of your procedure, you don't have any restriction regarding to the use of the electrolyzer, because in the case of the conventional electrolyzer with renewable energy, we have the restriction of the availability of wind energy or solar PV energy, or availability of surplus of energy in the system. Is my assumption right?
So first of all, it depends, since we are using wastewater as the fuel. So it depends on how many potential energy that is there from the wastewater.
Yes, but my understanding is that in your procedure, this procedure is continuous.
Yes,
however, when I use solar PV or wind energy, I need that we have this production or we have surplus of energy in the grid. For this situation, the electrolyzer is very, very expensive. And if you use the electrolyzer only 30%, is obviously is not an efficient procedure. However, my understanding is that your procedure is continuous, and this is very good in the sense that you produce hydrogen in continuous way.
Yes, that is correct.
Okay.
Which is why we propose to have it put in the wastewater treatment. So at the same time, it can create electricity, but also it also produces clean water from the wastewater. So it's very useful as well in remote areas. There's no power source there. We can make use of the waste.
Do you also produce oxygen?
Oxygen, yes, because it's one of the byproducts.
Yeah. Okay. Thank you.
Thank you all. We're now ready to hear from the fourth team. I would like to call the team from University, Escuela Politécnica de Ingeniería de Gijón, Universidad de Oviedo. Project Rewind, Viability Study for the Reutilization of Wind Turbine Blades at the end of their service life through alternative energy generation methods. Members, Pelayo Iglesias de Rueda, Mario Martín Blanco. Professor, Miguel Muñiz Calvente. Well done, team. All right, you may begin.
Okay, thank you very much. Well, hi, my name is Mario, and I'm here to present the Rewind project. Well, as we have seen in the introductory presentation, when wind turbines are at the end of their service life, they are treated as residues, and once dismantled, the blades are buried or left out to rot. Aware of the problem, efforts have been recently made to find uses for what is usually considered waste material. These solutions, although ingenious, are only band-aids due to the enormous amount of residue that will be produced. A large-scale, long-term solution must be found to reduce the unrecyclable wind turbine blades. The industry acknowledges this, and that is exactly what our project aims to tackle. Offering a solution based on the circularity of the wind energy technology by using the wind turbine blades for further generation of electricity, Rewind uses the waste an opportunity to keep generating value. The technical explanation. Well, our project is based in two basic principles, the vortex generation and the intrinsic natural frequencies of an object or a structure. For the first one, I'm sure that you have seen a vortex around an island, as you can see at the photo, or even around an airfall. This phenomena is around us in many situations. Based on the governing equations of fluid dynamics, when a fluid hits an obstacle, von Karman vortices are generated with a specific frequency which solely depends on the wind's speed. For the second one, I'm sure that you have heard about the Tacoma Narrows Bridge, and this occurs because any object, such as the street lights in this video, have an intrinsic characteristic, its natural vibration frequency. If the object is excited at that frequency, large displacements can be induced in its structure. And finally, when wind vortices are synchronized with the structure's natural frequency, we can take advantage of the resulting oscillations through a system consisting of alternators, coils, and permanent magnets to produce electricity. So the principal idea is that the vortex frequency and the natural frequencies must coincide, but the wind speed, as we know, is variable, and therefore the frequency of the generated vortices changes. A problem arises. How can we change the natural frequencies from a structure? Well, we can reach this by using a simple principle, similar to the one of a metronome that is around our daily life. The following animation shows this principle applied to a wind turbine blade. For this, we will use two different masses. The first one weighs 25 kilograms and will be placed on the base of the blade. By displacing the mass towards the top part, the harmonic frequency will decrease consistently. We can see that at the graph shown at the left. When using the 200 kilogram mass, the oscillation frequency is the same at the base, but as the weight is going to be displaced, the frequency decreases at a much higher rate. This is clearly visible in the graph shown at the left. With this simple system, oscillations can be maximized, and therefore the electricity produced. Many more mass stunning studies have been made at multiple blade locations, showing that the typical vortex frequencies can be easily achieved. Those typical vortex frequencies are in the range from 3-4 Earth to 8-9 Earth range. Conclusions. Well, the Canvas model has been used to identify the main partners of our project, Mqtt Protocol, such as EDP, Vortex Platelets, European governments, European Union. Also, the most important activities like taking grants from the Green New Deal, research and development, build a pilot plant, and key resources have been analyzed to propel the project forward. The proposed project estimates that the installation and operational costs are significantly lower with respect to those of conventional wind turbines. Rewind has a great advantage over other solutions dealing with retired wind turbine blades. The market and the infrastructures from the project already exist. This will also reduce costs related to the search for a market needs, customers, etc. The larger cost of the project is the opportunity cost of not moving forward with it. In conclusion, through innovation, circular economy, reduced cost, we find a solution to the blade waste problem, whilst reducing an expensive infrastructure such as the electricity grid by producing electricity. Thanks for your attention.
Thank you. And now, if there are any questions from the jury, this is the time.
I have a question. First, congratulations for your very nice project. And in fact, I have two questions. One is, how do you estimate, or how do you consider will be the life cycle of these retired blades? Because I believe that they will not last forever. So that is the first question.
Well, it's a good question. The boundary conditions are very different in this new operational of the blades. The conventional aerogenerators have high strains and stresses, and in our case, the critical locations will also be different. We propose to take advantage also of this situation with this new application of the blades by installing accelerometers to perform a continuous monitoring of the fatigue damage by operational model analysis. So with this technique, we could detect the crack nucleations and propagation by observing the changes of the natural frequencies. And we would be producing energy, and at the same time, we would be testing the blades and monitoring their fatigue resistance until failure in a very safe condition, because those accelerometers can't be installed in the conventional aerogenerators. And we will be also contributing to improving the industry's knowledge, and we could optimize the blades that are going to be built in the future. So it's a balance, you know, there's a balance.
Okay, I have another question about costs. Could you make some estimation of costs that could be necessary for an implementation of a project or for starting with a pilot?
Yeah, well, our estimations are around, for a pilot plant or a prototype, it's around 100,000 euros probably. But as I have said, we could have grants from the European New Deal or governments that would be interested in our project. So it's a profitable business because we already have the materials. So there's going to be profits in short term. So the pilot plant, the research initial cost is going to be very low because the material already exists and we will be producing energy.
Yeah, so when you mention 100,000 euros, of course, it's approximate estimate. And after a pilot, maybe, as you mentioned, material is already available, so maybe it's possible to decrease, right?
Mm-hmm.
Okay, thank you.
Thank you.
I'm sorry, but my question is basically the one that Telmo is just to did now about the cost of the prototype. Let me say in other words, if we will give you a blade, how much more money do you need to install a prototype?
Well, probably the same amount of money I have said before, about 100,000 of euros or 200,000 of euros. I don't think that could cost more. Probably if we build a pilot plant, we need more investment, but for a prototype, I think that is around those numbers.
A prototype with a full-scale blade?
Yes, well, yes.
We just retired 100 of blades from an ancient wind farm.
Well, you know what you have to do now.
100 of blades we already have. Thank you.
Okay, my question is about the amount of energy that is produced with this blade. What's the amount of energy that you can produce with this blade? Well, we have to take into account that about 35,000 of wind turbines in Europe will be retired in the next 5 years. So that makes about 100,000 of blades that will be retired in the next 5 years and will be ready for install with our application. So if we take in account that the wind speed average is around 36 kilometers per hour, and with our advanced simulations, we have reached about 15 and 20 kilowatts hour per day. If we multiply this number by the amount of blades that will be ready for the installation in the next 5 years, we could be talking about 2 gigawatts hour per day with what is now considered waste. So no, but my question is about one blade. Only one blade. The amount 15, 20 kilowatts hour per day. 15 or 20 kilowatts hour per day. Okay. And this use of the blade is not the original use for the blade when it was designed, and it's not the original design of a blade that is that it has this purpose from the very beginning. So you are using a design for a different use. No. My question is that you're using something, a piece of equipment that is going to work for a different use from his conventional design, and at the same time, it has not been designed for the use as a vortex. So what's the difference between the amount of energy you can produce with these blades and the blades that are specifically designed for use as a vortex blade? Your question is aligned with what this vortex blade is doing, or yes? The difference. My question is, how good are these blades compared to bladeless vortex equipment? Well, probably we should have to do slight modifications, like the structural stiffness should be changed, or probably the angle attack of the blades, or the weight. I don't know. We cannot say that how are they done, the blades is the perfect way to produce electricity by the generation of vortex, but with slight modifications of the material that already exist, I think that it's possible to generate the energy that I have said before.
you know, with slight modifications, it's not perfect, the geometry they have now, but with slight modifications, it could be possible.
Okay, thank you.
Let me just make one last question, sorry. When you were thinking about this idea, could you find some of these applications somewhere, or could you make some benchmark? Could you find something similar?
Well, there's a company that we say at the written project that we would like to cooperate with them, that is Vortex Plateless. They are doing something very similar with different geometries and different lengths, but using the same principle, the generation of the vortex. And something that is quite interesting is that they reach about 10 kilowatts hour per day as our estimations. So they are like the pioneers of this technique, but with different geometries, we can reach the same solution.
Okay, thank you.
I have a question. I mean, I think most of the questions are aligned, basically, but I think it's a beautiful idea. I'm not sure about the execution. And my question is, have you had conversations with Vortex Plateless? Because at the end, they have been 5 years investigating the technology.
Yes.
And as Luis has said, basically, they have 5 years studying, or maybe 10, because that started in 2012, studying what is the best equipment to produce the highest energy or to be more efficient. And now we are going to put a blade that has been designed for other means with slight modifications. And I think the question is, if you have conversation with them, if they told you, yeah, maybe this could be possible, we need to study it, and what is going to be the impact? Because Vortex Bladeless, one of the problems they have is the amount of energy that they produce, and then you're going to put a huge equipment aside from your company or whatever, and it needs to be efficient. I mean, that you need to produce a decent amount of energy. So that was my question. Sorry.
Well, we don't have talked with them, so we don't have their perspective about using this new design and this new geometry. But this is an idea. This is what I have said is that we don't have. We should try to watch if they work properly. And as I said, with the new Green Deal grants, with the help with the other governments, we could reduce the research and development cost, and the slight modifications that I'm suggesting could be found and could be put in the pilot plant or in the prototype. But in our advanced simulations, what is more important and what we have found in our simulations is if the structure natural frequency is aligned with the vortex frequency that is generated when the wind impact on the blade. For me, that's the main problem and the main wall we have to jump. So this first step is done. We know that it is possible to generate energy because those frequencies could be similar, could be the same, and that's how oscillations are made. So taking into account that, I could say that for me, in my perspective, it's very possible to make energy with great profits. I don't know if I have cleared your questions.
Okay. It's okay.
All right, thank you all. Lastly, the fifth top 5 team is from University, Instituto Superior Técnico, Portugal, Grenoble in P, Institute of Technology, France, Uppsala Universitet, Sweden, and the project is new integrated energy solution based on hybrid for renewable energy network. Members are Brandon Vargas Vera, Joao Saldana, Professor Elena Ramos. Congratulations. Are you ready? Go ahead.
Hello, everyone. Just let me check. I have the control. Yes. Okay. Have you ever heard about hydropower in the sea before? With HyperRun it's possible, and we want to tell you how it works. HyperRun is a new integrated energy solution to overcome different problems. Currently, all efforts are pointing out to beat climate change and decarbonize energy and energy production. For this, it is necessary to reduce renewables intermittency. With HyperRun, the energy sources are available when combining 4 different energy conversion technologies that can work continuously with the option to be off-grid or grid connected. And it is easily adaptable. And these are not the only problems that we can solve. Fossil fuel dependency and remote locations, and also disconnected from the grid areas. Most of renewables require large land areas for its implementation and viability. This hybrid energy converter appears as an innovative renewable technology solution, and the design is compact, flexible, and energy efficient. That being said, many of you must be wondering how it works, and here HyperRun is presented. This floating module is deployed in offshore conditions with strategically oriented PV solar in the top and well turbines on each side. This energy is enclosed with 2 well turbines extracting energy from the waves oscillation. This solution has a hydraulic circuit as one of the main innovative components. Water will enter to the upper reservoir, producing energy with turbines due to the head created between the sea level and the conducting pressure pipe. And this is going to be to the bottom reservoir. After that, water flow passes through the flexible pipe and check valve. And now part of the fluid can reach water air transient technology for energy storage, or WAT4S. That is based on water hammer to increase the pressure inside the WAT4S, allowing to efficiently pump water to the surface and store energy as compressed air, this without spending energy. The remaining water falls into the lower reservoir tank, and finally, with automatization and control, a set of valve switching can release the high pressure inside the WAT4S, boosting water from the lower tank to the surface again. Now, methodology is presented. First, we identified the limited flexibility of standalone renewables. The next step was to design the hybrid power plant with suitable technologies. In the bottom, we have some photos of the lab setup with the high RAM and WAT4S, where the operation was tested. Solar panels were integrated due to the natural cooling system of offshore conditions, and well-axis turbines present a good performance, and the wake effects are minimized. To prove technical and economical feasibility, the following results are presented. According to average wind, solar, and wave conditions in Portugal, all components were sized for different renewable technologies in different modules, in the module maximizing efficiency. We computed the power capacity, the energy produced per year, and the equipment required. In this slide are presented relevant numbers such as a positive NPV, a payback period of about 7.5 years that can be reduced with a commercial scale, and internal rate of return of 16%. Total installed power of each module is 23 kilowatts with a capacity factor of 62%. In addition, EDP renewables could avoid 120 tons of CO2 emissions per year. If 50 HyperRun modules are working together, it can produce around 7 gigawatts hour per year. These are several applications and sectors that could benefit from this energy produced. For water production, supporting desalination processes, and in result, irrigation as well. For hydrogen production, powering electrolysis. For offshore operations and flexibility to be installed in different conditions, including lakes and dams also. Finally, HyperRun, a profitable technology with low CapEx and OpEx, able to produce reliable energy a module easy to install, adapt, and scale, the most innovative hybrid energy plant in the world. That is just one pilot project towards to starting a new revolution in the energy market. Thank you so much.
Thank you. Members of the jury, any questions? No questions?
Hello.
Hello.
Congratulations for your very good project. When I was analyzing your estimate concerning the internal rate of return, it's 16%, so it's quite high. I would say it's a return rate that everyone would like to achieve. Can you elaborate a bit more about how you did your estimation costs and also your revenue costs so you could reach this figure in terms of the internal revenue rate?
Yeah, the thing is that the internal rate of return should be a bit lower, around 10%. The thing was that at the beginning, we evaluate the project with 5 years more. So maybe that's why the IRR is like higher. But we consider the lifetime of the project around 20 years. We took into account all the flow cash, also operation and maintenance cost. But I agree with you. In conclusion, I agree with you. The calculation that we put in the proposal should be like 3% less, but there's not too much difference.
Yeah. That was my understanding. Okay. Thank you.
Thank you so much.
Any other questions? No? All right, so thank you to all the groups for their presentations. And again, congratulations. Now the jury will gather once more for a few minutes to select the 3 winning projects for the 13th edition of the EDPR University Challenge. Stay connected and see you in a few moments.
The world has changed. I feel it in the water. I feel it in the earth. I smell it in the air. A new power is traveling all around the earth. A clean and infinite energy in constant renovation that comes from natural sources such as the sun, the wind, and the human will. Yes, the world has changed. I feel it everywhere. Many men and women have started to go in a new direction, innovating to make humankind grow while nature is preserved. This community is EDPR's people. We are present in 15 countries, and together we have increased the production of natural energy, generating 29 terawatts-hour, avoiding 18.5 million tons of CO2 emissions, and growing day by day to achieve a wealthy business while contributing to a cleaner air. That's the result of putting together the nature power and a total trust in people's energy. Our energy is more than 1,700 employees from 32 nationalities. Our partners, shareholders, clients, the communities that live happier through our social, economical, and environmental initiatives. Now, we are a bigger company with a stronger capacity. The sun, the wind, and the sea help us in our aim. They don't need to change, but we, humans, must keep evolving, and we have to do it now. We must do it together, because our mission is not just the EDPR's mission. It's the future that we all deserve. It's time to join our community, the community of change.
From today onwards, the sun will shine in a different way. It's about to be transformed into clean, renewable energy. And that energy will improve the lives of thousands of people. The planet can't wait any longer. Here at EDP Group, we're doing our bit. We're a global energy company committed to leading the energy transition and improving the lives of current and future generations. EDP Renewables is launching the company's latest solar complex in Brazil. Pereira Barreto Solar Complex is the largest in operation in São Paulo state and the 5th largest in Brazil. The complex covers a total of 455 hectares and can generate up to 547,000 megawatts hour per year. That's enough to power a city of approximately 750,000 people. In just 1 year, the photovoltaic complex will stop more than 150,000 tons of CO2 from being emitted into the atmosphere. It'll also make a lasting contribution to the region's social and economic development. At EDP, we believe that a sustainable future begins with the choices we make today. And we're changing tomorrow now.
This is a new way of generating energy and an important step to fight against climate change. Portugal enters in a new era with an international acclaimed solution in the production of offshore renewable energy. The Wind-Float Atlantic project, formed by Ocean Winds, Repsol and Principal Power, is the first floating wind farm in continental Europe just off the coast of Viana do Castelo. This floating wind farm will allow the optimization of natural resources and will speed up the commercial deployment of this innovative technology. Wind-Float Atlantic is an example of a more sustainable future for mankind, with the largest turbines ever installed on floating platforms. The total installed capacity of 25 megawatts will provide sufficient energy to 60,000 people throughout the year. This energy promises an endless source. The potential of wind is immense, and this renewable energy is an essential part of the worldwide decarbonization strategy, free of CO2 emissions. The Wind-Float Atlantic project is the future we envision. Our mission has begun, and we will continue to nurture the power of nature to make our planet more sustainable. This is the beginning of a new era committed to enabling a better future. Wind-Float Atlantic. Energy beyond the horizon.
The world has changed. I feel it in the water. I feel it in the earth. I smell it in the air. A new power is traveling all around the Earth. A clean and infinite energy in constant renovation that comes from natural sources such as the sun, the wind, and the human will. Yes, the world has changed. I feel it everywhere. Many men and women have started to go in a new direction, innovating to make humankind grow while nature is preserved. This community is EDPR's people. We are present in 15 countries, and together we have increased the production of natural energy, generating 29 terawatts-hour, avoiding 18.5 million tons of CO2 emissions, and growing day by day to achieve a wealthy business while contributing to a cleaner air. That's the result of putting together the nature power and a total trust in people's energy. Our energy is more than 1,700 employees from 32 nationalities. Our partners, shareholders, clients, the communities that live happier through our social, economical, and environmental initiatives. Now, we are a bigger company with a stronger capacity. The sun, the wind, and the sea help us in our aim. They don't need to change. But we, humans, must keep evolving. And we have to do it now. We must do it together. Because our mission is not just the EDPR's mission. It's the future that we all deserve. It's time to join our community. The community of change.
From today onwards, the sun will shine in a different way. It's about to be transformed into clean, renewable energy. And that energy will improve the lives of thousands of people. The planet can't wait any longer. Here at EDP Group, we're doing our bit. We're a global energy company committed to leading the energy transition and improving the lives of current and future generations. EDP Renewables is launching the company's latest solar complex in Brazil. Pereira Barreto Solar Complex is the largest in operation in São Paulo state and the 5th largest in Brazil. The complex covers a total of 455 hectares and can generate up to 547,000 megawatts-hour per year. That's enough to power a city of approximately 750,000 people. In just 1 year, the photovoltaic complex will stop more than 150,000 tons of CO2 from being emitted into the atmosphere. It'll also make a lasting contribution to the region's social and economic development. At EDP, we believe that a sustainable future begins with the choices we make today. And we're changing tomorrow now.
This is a new way of generating energy and an important step to fight against climate change. Portugal enters in a new era with an international acclaimed solution in the production of offshore renewable energy. The Wind Float Atlantic project, formed by Ocean Winds, Repsol and Principal Power, is the first floating wind farm in continental Europe just off the coast of Viana do Castelo. This floating wind farm will allow the optimization of natural resources and will speed up the commercial deployment of this innovative technology. WindFloat Atlantic is an example of a more sustainable future for mankind, with the largest turbines ever installed on floating platforms. The total installed capacity of 25 megawatts will provide sufficient energy to 60,000 people throughout the year. This energy promises an endless source. The potential of wind is immense, and this renewable energy is an essential part of the worldwide decarbonization strategy, free of CO2 emissions. The WindFloat Atlantic project is the future we envision. Our mission has begun, and we will continue to nurture the power of nature to make our planet more sustainable. This is the beginning of a new era committed to enabling a better future. WindFloat Atlantic. Energy beyond the horizon.
The world has changed. I feel it in the water. I feel it in the earth. I smell it in the air. A new power is traveling all around the earth. A clean and infinite energy in constant renovation that comes from natural sources, such as the sun, the wind.
Welcome back again. Now the time has come to find out the winner of the EDPR University Challenge 2021, as well as the teams in second and third place. The winner will receive an award of 6,000 euros and the coordinating professor will receive 3,000 euros. The runner-up will receive an award of 3,000 euros and the coordinating professor will receive 1,500 euros. The team that comes in third place will receive an award of 2,000 euros and the coordinating professor will receive 1,000 euros. But before we meet this edition's winners, I would like to ask Mr. Miguel Stilwell Andrade, CEO of EDP and EDPR, to share a few words with us. Miguel?
Thank you, and thank you everyone on the call, and congratulations to everyone who did the presentations today. I'd definitely like to thank not only the students, but the teachers, the members of the jury, all of the people who have been participating from the different universities and well, everyone else who's taking part, I think, in this event today. I mean, for me personally, it's a pleasure to be able to take part in this presentation today, on this session today. Clearly, it is something which has been going on for a number of years, I think, with considerable success. And so I just wanted to congratulate also the promoters of this and the team that's been working to put this together. You know, I think the EDPR University Challenge Awards is really something that has managed to be consolidated over time and is something that is widely recognized by the different universities and the students as something that can add value. I mean, I would definitely like to take the opportunity to talk a little bit just about how we are seeing the world. I mean, we at EDP and EDPR are firmly convinced that we are in the stage of an energy transition, which has really revolutionized the energy sector. If we look at the Paris Agreement, we are talking about 195 countries coming together and signing a commitment to reduce emissions to net zero by 2050. So this is a major commitment by all of the different countries. Some are moving faster than others, but I think that's something that is just a global commitment. We on our side, as you know, have been committing to go to net zero by 2030, so anticipating the targets by 20 years. We've been committing to go to coal-free by 2025, and we've been investing heavily in renewable energy, not only over the last years, but we have an ambitious plan to invest approximately 24 billion euros over the next 5 years. So building 20 gigawatts of renewable energy in this period. And I think one of the key things which for me really stands out is that over the next couple of years, we are going to need a huge amount of innovation in the sector. One of the most interesting documents which I think came out over the last couple of months was the report by the IEA, the International Energy Agency, talking about how we could get to net zero by 2050. It's very interesting because they talk about obviously the electrification, the decarbonization of the energy sector. They talk about hydrogen. They talk about essentially reducing or increasing the energy efficiency. But one of the key things is they also talk about new technologies and new business models and how they will act. That there are a lot of things which still need to be adopted, that still need to be discovered to actually be able to make it to net zero by 2050. So there is a lot of work to be done in this sector, a lot of investment to be done, but a lot of innovation to be done also over the next couple of years. And I think, challenges like this and really thinking a little bit about the future is absolutely key to make sure that we are able to reach those targets. So we as a company and as a team are completely committed to this objective. As I said, we are the most ambitious utility in terms of reduction of emissions over the next couple of years. We are investing not only in sustainable growth, but we are also investing to be a reference in ESG, so environmental, social, and governance. We've been number 1 and number 2 of the Dow Jones Sustainability Index over the last 10 years. And I think that's something that also leaves us particularly proud, because I think sustainability is now a precondition to be able to operate on a long-term basis. And I think that's something that we at EDP and EDPR have really been doing over the last couple of years, and it's a firm commitment also going forward. So I definitely invite all of you to continue to innovate, to continue to come up with good ideas. Thank you very much to the jury for having basically participated in this and having put in the work to look through all of the different projects. I'm sure that everyone that is on the call is anxious to know what they have deliberated and what is their verdict. So without taking any more of your time, I'd pass over the word to the jury or basically so that we can know who is this year's winner. So good luck, everyone, and thank you for having me.
Thank you very much for your words, Miguel. And now, let's meet the winners. Please welcome Enrique de Oeijo, who is going to announce the team in 3rd place. Enrique?
Hello, good morning. The 3rd prize goes to the Escuela Politécnica de Gijón. The project is the number 1. That is the project focused on the smart EV charging point. Congratulations.
Congratulations indeed, team. And now, to announce the runner-up of the EDPR University Challenge 2021, 2nd place, please welcome Luis Santos.
I am not Luis Santos, I am Joaquín García, but it's the same. I am going to announce the number of the 2nd place in this question. The 2nd place is for the Rewind project from the Escuela Politécnica de Ingeniería de Gijón. Congratulations.
Congratulations. And to announce the winner of the EDPR University Challenge 2021, Please welcome Telmo Vieira.
And the big winner of this 13th edition of EDPR University Challenge is Waste to Hydrogen from different faculties, UPC de Barcelona, TUV Eindhoven, from Netherlands, ESAVE, AG Lisboa, and Poland. So congratulations.
Congratulations to them, and congratulations to all the groups that have participated in the ceremony. Thank you very much to all the participants, professors, assistants, guests, and of course, EDPR for making this initiative possible for the past 13 years. Next year, we will all come together again to meet another group of brilliant students who will undoubtedly dazzle us with the new and innovative ideas. We say goodbye with the hope that next year we will be able to hold a ceremony where we all be together in person. So thank you, everyone. See you again next year at the next edition of the EDPR University Challenge. Bye now.